So here is another question on energy associated with simple harmonic motion. So it is given that a mass of 0.5 kg is connected to a light spring of force constant 20 Newton per meter. So it is oscillating on a horizontal frictionless surface. We have to calculate the total energy of the system and the maximum speed if the amplitude of this SHM motion is 3 centimeters. Second bit, we have to find the velocity of the mass when the displacement, the instantaneous position, is equal to 2 centimeter. And we have to find the kinetic and potential energies of the system for the same displacement, that is equal to 2 centimeter. Okay, so this is the whole thing. So we have a horizontal frictionless surface. On that we have a mass, let's say an object of mass m, which is connected to a spring. Okay, so let's say this is the equilibrium position. Okay, so here it is moving in a horizontal position, so let's say this is the equilibrium position, and this is the maximum it can go either way. So that is equal to 3 centimeter and here minus 3 centimeter, like that. This is the thing. Mass is equal to how much? 0.5 kg. Spring constant K is equal to 20 Newton per meter. Okay. Now, first it has been asked to calculate the total energy. Now we know that the total energy is equal to the potential energy plus kinetic energy at any position. So that is equal to 1/2 k x square, which is the potential energy, and 1/2 k a square minus x square. So 1/2 kx square minus 1/2 kx square, they get cancelled out, so it becomes 1/2 k a square. Here the amplitude of oscillation A is equal to 3 centimeters. Okay, A is equal to 3 centimeters. So the total energy is this much. We simply have to substitute A with 3 centimeter, that is 1/2 into k 20 into 3 into 10 to the power minus 2, converting it into meter. So it becomes 9 into 10 to the power minus 3 joules. This is the total energy, okay, which is constant, always constant throughout the SHM motion, which we have discussed many times in the previous questions too. Next, in the same bit, it is asked to find the maximum speed. Okay, there are two ways we can do this. I will show you both. First is the straightforward way. We know that for SHM, the maximum velocity or speed, that is equal to omega into A. A is the amplitude, omega is the angular frequency. Here omega is not given, so we have to calculate it. So omega is equal to root over of k by m, spring constant by mass root over, equal to 20 by 0.5. So which is basically equal to root over of 40 radians per second. So which is coming around, if we calculate the decimal value, it is coming around 6.324 radians per second. Now the maximum speed or velocity will be equal to 6.324 into A amplitude, which is 3 centimeter, converting into meter, 3 into 10 to the power minus 2, that is equal to, it is coming 0.19 meter per second. So this is the first way. Another way we can do this is, see, the kinetic energy, it will have maximum value when velocity will be maximum. Okay, when velocity will be maximum. Okay, now when kinetic energy will be maximum, the maximum value, at that point potential energy will be 0 joule. But the sum of the kinetic energy and potential energy, it is always constant, that is equal to 9 into 10 to the power minus 3 joule, which means that when the kinetic energy is maximum, its value will be equal to 9 into 10 to the power minus 3 joules, which means 1/2 mass of the body, which is 0.5 kg into V square max, is equal to 9 into 10 to the power minus 3. That implies V square max is equal to 9 into 10 to the power minus 3 into 2 by 0.5, or V max is equal to root over of the above thing, that is 9 into 10 to the power minus 3 into 2 by 0.5. Okay, this. So this becomes how much? That is equal to also 0.19 meter per second. Same thing. Okay, this is also same. So here both ways we are getting the same value of maximum velocity. So either way you can proceed. Next, it has been asked to find the velocity of the mass when the displacement is equal to 2 centimeters. So here we know the basic formula. At a particular position, velocity is given by omega into root over of a square minus x square. A is the amplitude, x is the instantaneous position, omega is the angular frequency. Angular frequency value I have calculated. It is 6.324 radians per second into A, the amplitude, which is 3 centimeter, 3 into minus 2 whole square minus 2 into 10 to the power minus 2 whole square. Okay, this much. So it is coming around 0.14 meters per second. Okay, this. Then it has been asked to find the kinetic and potential energies of the system when the displacement equals 2 centimeters. So this is the second bit. Then the third bit, the kinetic and potential energies of the system when the displacement is 2 centimeter. So potential energy, we all know, 1/2 kx square equal to 1/2, which is equal to how much? 20 Newton per meter. That is the spring constant, I think. Yes, 20 Newton per meter, and x square is 2 into 10 to the power minus 2 whole square. So it is coming around 4 into 10 to the power minus 3 joules. Kinetic energy, that is equal to 1 half k a square minus x square equal to 1 half into 20 a square, which is equal to 3 into 10 to the power minus 2 whole square minus x square, which is 2 into 10 to the power minus 2 whole square. So this is coming around 5 into 10 to the power minus 3 joule. Now at this point, okay, at this point if we add these two, okay, potential energy plus the kinetic energy, the total is equal to 9 into 10 to the power minus 3 joules, the total energy, which is equal to the same thing, 9 into 10 to the power minus 3 joules, which we have already calculated previously in the first case. So like I said, in the different questions that we have solved until now related to energy, this thing we have highlighted many times, that the total energy of the system throughout the SHM motion, it is constant. Okay, so this is the thing. So here we have solved.